Noķēra dejotājs. Forši sanāk. Here are PMMA microspheres, 15 microns. I dip needle. Here is Van de Graaff generator from cola bottle. I used it to charge dust. And now can throw dust into quadrupole trap. Here we see trapped ions. Box made from microscope slides. And here are ions from microscope. Cool. Here loading one more time. Ion trap is sitting on the box with transformer, which gets warm, and that helps electrostatics to dry air. Then move ions around with Van de Graaff.
Very interesting dynamics. Some particles hit other, change the charge and move to other end, and then hit and come back. They like to travel electrostatically.
Transformer is from a microwave oven in a PC power supply box, and there are several resistors in series, total resistance 20 megaohms.
Spent 2 days by rebuilding a Paul trap made by Esco's Labs, Oliver Keller. Electrodes are also 3D printed, taped with copper tape.
Making black conductive surface on acetylene flame. Here is the result. This is now the trap arrangement. Here we go, we get some dancers. There is still wind moving the things around. Now we have many dancers, but they don't like the wind. As the voltage changes, particles are repelled by Coulomb repulsion, and that's why we have tracks in all directions. I touch one electrode with the finger of these end caps, and we see electric charging immediately. Similar thing happens if I scratch upper electrode on a plastic surface. Now I have positive 30 volts connected to upper electrode, 0, positive 30, 0, positive 30. So we have electrostatic voltmeter, 0 volts, 30 volts, 0 volts, 30 volts. Here comes most interesting thing for today. If it's only a single particle in the trap, I can apply DC voltage to end electrode and compensate micromotion. It becomes 0, which is good for making microdrop lasers, probably. Micromotion compensation, too little voltage, too much voltage, too little, too much. And here in the middle, it's still. Now comes size measurement with telecom fiber, until 25 microns. We see that fiber is charged up as well. With free particles in the trap, we cannot cancel the micro motion. Particles feel static electricity outside. Better material should be used for walls, which is conducting. Now spraying ions from a needle conductor from one the graph generator. We push everything away. The ions with a needle from one the graph generator. It's like ion wind. Positive ions. And we lost all particles. Now we have a large particle. It does not feel DC electric field so much. 30 volts is not enough. Added high voltage DC power supply, which can give 1200 volts. And now can balance the heavy particle against micromotion. Cannot balance in all dimensions because of stray electric field. You can probably shoot it out of trap.
For me, it was very important to get clear with the numbers. From a two equation, we get such parameter Q, and it should be between 0 and 0.9 for particle to be stable in the trap. But there are very few numerical examples, so it is not clear if to use CGS system or if to use SI system. And it appears that we should use SI system. And we calculated E over M, and then we approximate that Q about 1 is stable, and from here we get angular frequency squared. Such expression here is Q over M, and here is electric field made by quadrupole rods. And the typical value V over R squared is 1000 volts per square centimeter, and we need to convert to meters squared. We get 10 to 7, and now we can easily calculate omega squared. And then we get omega, and get frequency omega by 2 pi. And for electron we get about 300 megahertz, which matches value in the publication. Next we calculate the same thing for proton. Proton mass is 1000 times larger than electron mass, so E over M ratio becomes 10 to 7, and then we calculate omega squared, omega, and frequency we get 7 megahertz. Afterwards we calculate for uranium-238. It has 92 protons and 141 neutrons. Total sum is 238 of heavy particles, and mass is 4 times 10 to minus 25 kilograms. Q over M is 4 times 10 to 5, and then we calculate frequency and get 330 kilohertz. And finally we do the same for 20 micrometer diameter aluminum particle, which is charged with 350,000 electrons. And we calculated Q, we calculated mass from density and volume, and we get 10 to minus 11 kilograms, or 10 to minus 8 grams, or 10 nanograms. Then we calculate Q over M, and we get 0.005. And afterwards angular frequency squared, where we insert the value from previous 10 to 7, and we get omega 316 radians, or frequency 50 hertz. So we can use our 50 hertz transformer to trap aluminum particle, which is okay. And then we do some side calculation. Let's calculate the voltage at surface of aluminum. We have 10 micrometer radius, and here is electrostatic formula, and we get 50 volts, same as in the paper. And from Van der Graaf generators, there is expression that maximum voltage is 30 kilovolts times radius in centimeters. When corona discharge happens and voltage does not rise higher. So we put the numbers for aluminum dust, and we get 30 volts, which is close to 50 volts, and that means that we cannot charge micrometer dust to kilovolt voltages. And final exercise is to calculate Millikan drop experiment, and the final exercise will be to calculate the Millikan oil drop experiment, where electric force is Q times electric field intensity, and intensity is voltage over distance. We choose 1 centimeter separation between electrodes and 1000 volts voltage. Then we get intensity 10 to 5 volts per meter, and electric force 5 times 10 to minus 9 newtons. Previously we calculated that mass of our aluminum particle is 10 to minus 11 kilograms. That makes 10 to minus 10 newtons. And we see that electric force is about 50 times larger than our gravity force. So actually one needs smaller voltage between the electrodes. And the final calculation will be to get the number of atoms in 20 micrometer aluminum sphere. Previously we calculated the mass, 10 to minus 11 kilograms aluminum atom mass, and we get 2 times 10 to 14th power atoms, which is a huge number.